Can you hear this, Sarah? Or Shannon?
Yes, I
we
can.
hear you.
Okay, all right, great, thanks. Let's see. So there's a couple papers. I mean, I tried to find some things on scattering. I found quite a few things, but these two, this thing seemed to be close to what kind of what we were doing. So they've done. They started out with studies on let's see, on micelles. This is sodium dodecyl sulfate and then polyethylene oxide, PEO. So let's see, let me go over here. So, let's see. So so it's SDS. It's also called SL, sodium lauryl sulfate. So it's like, so it's like 12 carbons and then a sulfate group. And so and then sodium. Plus here. That's SO3. This work. Should be SO3. Something like that, I guess. But anyway, so this is a polar head group. This is in a nonpolar tail. It's usually people like kind of make it like that. And then so you have water. You throw some of this into it. Well, immediately, like it does this at the surface of the water. Right? You'll just cover that with a monolayer if you can. Then there'll be some left over that are in here. These things have like KT, so they're moving around. So it wants to, like, as temperature goes up, it wants to kind of balance between the surface ones and the ones in the water. That's when the concentration is less than 0.2 weight% of this SDS. And then when you get above 0.2 weight%, those things can meet each other. In other words, they're so dilute that they never come in contact with each other. Below that and above that, they come in contact with each other. And there's like kind of a heat of micellization. So almost like a crystallization, right? And they're going to form spheres. And then so that's micellization. So then you have a competition between the surface ones, the ones that are just floating around, and then these micelles. It's like a three-way competition. There's going to be some population of each one. Because of this heat of micellization, like these are favored. I mean, the surface ones and these are favored, and the ones that are free aren't favored. So if temperature goes up, you'll get more into the solution. So you can get this thing called a Kraft temperature, where you can break apart the micelles basically. Right? So anyway, so this is a thermodynamic balance set up with that, and then you have PEO, which is this thing. So it's polyethylene with some oxygen in it. This is the ether linkage, and that's got a negative charge, so that's soluble in water below 60 degrees C. That goes in water. Above that, it separates. So because water's got a positive charge on it. So they. Oh, okay. I heard something fly across the room. So anyway, so they're mixing these together and they interact with each other. Right? So that's kind of a standard thing. So they got like this scheme. So you can have like free polymer, you can have free surfactant, you have the micelles. So if you put in oil, like it'll go into the middle. So dirt's kind of oil, so dirt goes in the middle. So this is kind of a detergent. And that also changes the shape of the thing. Also, if you change like the polarity of the solvent, so if you put in an alcohol, here they're using isopropanol, right? So you put propanol in, that can displace the water that's bound to the surface. It can displace the surfactants in the micelles. That's what they're saying. So you have this set up, and then you're going to put in this alcohol. So it's like that guy, this is polar, this is non-polar. So it kind of looks like a surfactant almost. It'll kind of sit there like that. Right? And then you have these negative sulfate groups. So it kind of could displace, I mean, that changes the shape. Oh, sorry. Yeah. So that this isopropanol can, so it's going to be, so that can displace some of the surfactant. It can change the shape of the micelle. It can actually break apart the micelle. So some kind of, also some of these will be sitting here, kind of, I guess that's negative charge. This is non-charged. So they don't really interact like water does. Water is going to be all over here. And the sodium counterion. So it'll be a counterion cloud around it. So basically it's kind of a complicated thing. Entropically, there's a lot of things going on. Anyway, so they want to make structures with that. And this starts to look like how like DNA is read to make proteins in the ribosome kind of thing, but also just that you can make like a bead pearl necklace with the micelles, something that's been around as a concept for a while. So they're trying to see structurally what happens. So they have these polymer chains, and they have the chains tagged to the. So they're using, so for our purposes, they're using the Debye equation, right? This equation. That's so X is Q squared RG squared down here. And then that's the function Debye came up with for a Gaussian polymer chain, right? Theta solvent. So unfortunately, like PEO in water isn't a theta solvent at all. It's like a good solvent. It's a really good solvent. So this function doesn't work for that. That's one problem here. Then they throw in a couple of fudge factors, like they have a background term, and then they have this power law term that they've introduced that accounts for anything like dirt or whatever. So it's like, see how this tail's up over here? So that power law term is supposedly going to account for that tail up over here. But it's got like two parameters in it. So you're adding two kind of free parameters to your fit, like this IPE and this PE. So you're adding parameters to the fit, or here IP and Q and P, right? So there's two parameters you add to the fit that makes it more complicated, plus the background. Then they just throw this into a blender and they get their answers out, right? So one problem with this is that if you take their data, so they show some data here, like they have dilute 0.2 weight percent P polyethylene oxide and deuterated water. That should just be the chain, right? So if you digitize that thing, you come out with this. So then you just draw some lines on it. So this dark line is a 5/3 for good solvent. It's a perfect match for it. So that's not the function they're using. The function they're using is this dashed line, which is power 2. That doesn't match it at all. And with this, you can even see like the persistence in the data. There's some little background, but basically the persistence length is like right there. So you can get it pretty easily from the data. And then there's a coil size there. And then as concentration goes up, you expect to see screening of this. We plot intensity divided by concentration. This would drop down here. And that would give you this kind of enthalpic interaction number, like the second Vero coefficient. Right, but so they didn't do that either. Actually, I didn't ask a question about that, but they didn't do that either. So they didn't really, so they're going into concentration series, but they don't account for that thermodynamic feature of it. Anyway, there's a lot of problems with how they do their fits. So that's what the quiz is about, is like saying like how do you do, what's wrong with these fits. So not only that, but the function they really use to fit that is this function, which is the Ornstein-Zernike function, which they call the Lorentzian. It can also be called Lorentzian because it's got, if you use m as 2, which is for a Gaussian chain, it's true, but we know that doesn't work. Like if you compare the limits of this function with the actual function, the bifunction, they're at the same limit, so it doesn't really work. In fact, if you compare the two, you'll get this equation that Rg, for the Guinier part, that Rg squared root of 2 times this correlation length. Right. So anyway, the quiz is mostly to like pick apart how this is so screwed up, you know. Then they also, so they say that this correlation length describes average distance between two polymer chains. So, like if you go in semi-dilute solution, so first off, it describes the coil size, right? It isn't, I mean, if anything, it's describing the coil size. Secondly, if you're, even as how they're proposed to use it, you know, let's see. Cam, this guy's got a slower response than me. All right, so there's a problem with going to the semi-dilute solution. And you have to have dilute, you have the coils, and then you go to semi-dilute, then the coils overlap. Right? So you end up with this kind of thing like that. So that's the thing you're looking at. So there's no coil. There's no coil to see unless you tag one of the chains. So you could see one coil if you deuterate one chain, but that's not what they did. They deuterate the solvent. Right, so you can't see a coil at all. Like there's no coil there. So there's no distance between coils. In other words, if you can't see a coil, you can't see the distance between coils. So what they're seeing is this blob size. Right? So they don't want to say blob, I guess, or who knows what. But I mean, the thing that you observe would be like blob size. If this was a function that could fit that, which it isn't, then that number would be the blob size. And then that would have something to do with the thermodynamics of the thing. Right, because we figured out what the concentration blob, how you get that. So it kind of ignored like most of polymer science, then ad hoc. So there's a software you can use called SASFit, right? That has like every function that's ever been proposed in it. And it's written by, it started out at NIST in Washington, and then it kind of, the Swiss have been doing it. There's a guy at the Swiss neutron source that kind of takes care of it as far as I know. So, and also there's a couple other people that have been, so it's like a group contribution thing for a fitting function and has all the functions in it. So anyway, so it's got these functions, it's got the ability to like arbitrarily add together functions. So you can add together a power law with this. So the problem with that is that if you add these together like this, so they're just kind of, they do a series of adding togethers here. Here's another add together, right? So whenever you add two things together, you're assuming that the two things are independent of each other. They're completely independent. So as if, and I write this in the quiz. So if you have this thing, right, and then these micelles somehow like that, then you're saying that that's equal to those micelles, and then this thing in separate containers and you shoot the beam through it. And then you can just sum the intensities of the two and get the result. But if the micelles are charged, and these polymer chains are charged, first the charges interact with each other, right? So the structure isn't going to be the same as if you had polymers and micelles and just add them together. So he's got I for the polymers, he's got I for the micelles, and he sums those two together to get his intensity. What he's missing is how the polymers interact with the micelles. In other words, if the micelles formed a crystal, which they can make a colloidal crystal, then the polymer would be trapped in kind of an organized fashion, and you get a diffraction peak from the polymer. Right? So this kind of sum would ignore that kind of thing. And that's an extreme of it. But basically, the fact that they're interacting means they organize each other. The micelles move to different places, and the polymers move to different places too. And that's going to give rise to some other intensity, like something that couples these things. And also the original intensities probably won't be the same in that condition. In other words, maybe it's not going to be a self-voiding walk at that point. It's going to be something else like a rod. It might change. The fact that the micelles there could change it to a rod, or it could do other things, right? So you don't know what it does. So you can't. So that idea of just adding it together is, you have to justify it. You can't just say, I'm going to just add these together, So is that, and then this function, we did this limits of this. You can go to high Q, then you can get Q to the -2 because they're using 2 here, because of Q, if it's high Q eta that's bigger than 1, then the 1 goes away. You just have that power law. And at low Q, when this is small, you can say that's the same as exponential of Q eta squared, Q squared eta squared. And then it's 1 over, so it's minus Q squared eta squared. So it kind of looks like Guinet's law, right, in the low Q limit. The problem is when you do that, you get this thing for RG, and if you do it for the power law, you don't get the same relationship. So it doesn't duplicate this function. So they're not the same function. The power law is different, or the Guinet is different, but they aren't right. And this isn't, that's not RG either. That's not true what they say here. I mean, in other words, it's true for the limit of low Q. It's not the right thing to do, so it's just like trip down, go through this stuff. This is one from this year. So same group. This Marina Sai-Nu, it's a Greek name I can't pronounce, but she's at Buffalo. And she does, it's good work, it's interesting. So it's basically something similar to that, except instead of using polyethylene oxide, they're using pluronic. So it's polyethylene oxide and then polypropylene oxide, the red thing, and then polyethylene oxide. So this is the polypropylene at room temperature is insoluble in water, so it'll go into the core. In other words, it's hydrophobic. The polyethylene oxide at room temperature is hydrophilic. So you can kind of create these hairy micelles if you want to do that. So it's kind of interesting. And she's demonstrating that happens using neutron scattering, using the same kind of routine, like the same functions. So this is the same guy. Then it's two. It's got that weird power law thing. And then you come to this business, which I don't ask much about. So again, it's like this sum. It's this sum thing assumes that the things are completely, absolutely independent of each other. There's no interaction between the things, right? So you're just saying this is in a separate bottle, that's in a separate bottle. And the beam happens to go through all the bottles, and then it comes out. So you add them together, right? Otherwise, it's a much more complicated situation, right? So anyway, so there's that business. So these are the curves. They don't look anything like what we've been looking at. So why is that? So, right. So this is because there's two reasons why these look so weird. So if you have, like we've been dealing with like this thing, it's got no perfect size. In fact, we know that this is going to be like, there's a probability that end-to-end distance right? And it's going to be Gaussian. It says there's no size to this thing at all. It's just like moving around. There's a Kuhn length, which is also a statistical number. And then there's like kind of a radius to it. It could have a fixed size, I guess, but it turns out somehow it doesn't. So you never see anything like a peak out of this. So, but if it is perfect, if they have perfect spheres, then you have this issue. So we got this scattering distance R thing. That was our fringe pattern. So we have the thing going in, the thing going out. There's a fringe pattern that shows up as this distance in vector R. It's normal to the direction you're looking at, normal to the planes that are diffracting. And so, right, so we have this vector R that has to do with the angle. That R goes up and the angle goes down. It's inverse space. So, so you can throw that R onto your sphere, right? And so you know that, like, if you go double R, there's one in between that would kill it. So there's no scattering from the middle part of a solid sphere. And then you get scattering from the interface. We figured out that would give you Q to the minus 4. But power law, just from counting up what the amount of material is a function of R. In other words, as R gets larger, you get as R gets larger, you get less. The n squared goes up, but number goes down. So the overall intensity, so that would give you the intensity that's proportional to, that would give you R to the 4. And in inverse, if you go to Q, that's Q to the minus 4. You get the intensity decays of Q to the minus 4. Right, so anyway, so we got that. But basically, if it's a perfect sphere, that's true of anything that has a surface. Like it could be something that's not perfect that has a surface. You know, so kind of Loch Ness monster. Right? No, wait, that's a duck. There could be a duck. So, right, so R will at some point reach D, right? And then there's like a delta function. Like you go from nothing to like something all of a sudden, like off a cliff. Right. So that kind of feature when you have a perfect, and also say you had a perfect protein. It's got a perfect size. So that's got several of these, right? Several of these perfect sizes. It doesn't matter if it's spinning around, it's got a perfect size. That means that the density function, say electron density, is going to like go through a cliff. So Fourier transform of a cliff is a peak. Okay, so you're going to get kind of a peak from anything where you have a perfect structure. Polymer has no perfect structure, you don't get a peak. But anything that's like a sphere, you get a peak, and my cells are spheres. So they're kind of complicated spheres. They're going to have, for X-rays, okay, so X-rays look at electron densities. So you have like sodium ions are metal, you know, that's got a huge electron density. Then you have this organic stuff. So you're going to have a organic shell around it. And then you're going to have this hydrocarbon center to it. See, I mean, sulfate, and then sodium, and hydrocarbon. Right. So for X-rays, it doesn't see any of this. X-ray is only going to see. I lost my red pen someplace there. So X-ray will only see these sodium. What it will see is like this kind of cloud of sodium around it, and the rest of it won't see. Then neutron, sodium's invisible. So neutron's only going to see like this kind of core shell structure. The two things will see different things. So neutron, the core shell structure is going to have, so if it was some odd object without this perfect size, we'd expect to see a curve like this, like -4 power law and then Guinea's law. And there'd be like a need of this because it's got the lowest possible, the prefactor of the surface to volume ratio. So the sphere has the lowest possible surface to volume. The maximum possible would be like here. And so you go up, you get more surface to volume. The sphere has the lowest possible, so it'd be like that. Then if you have, but if it's a perfect, then the radius, so this is RG, which is square root of 3/5 of the radius, right? So the radius is going to show up like a peak here. So it's going to be like, oh, there's a first order radius. It's like Q. There's a second order radius, third, fourth. So it's like 2Q, 3Q, 4Q stars, right, for the radius. 2 pi over the kind of the radius of the thing. So that's kind of combined with the two. So you'll get this decay, get this oscillation. It's going down -4, and then you'll see kind of a Guinea tailover, but there's this oscillation is embedded in it. So that's one source of the peaks here. They're modeling. So if you add more surfactant into the system, they go from spherical to ellipsoidal. And then finally, if you put enough in, they'll make worm-like micelles that are like 100 micron long, like a human, looks like a human hair. You can see them in a TEM, like cryo TEM, right? So, all right, so they're like, these would be like 40 angstrom diameter and then like 100 micron long. So they entangle. That's shampoo. That's like when the shampoo comes out, it's got viscoelastic properties. You get dye swell and everything with it. So that's all right. So you can do that by adding more salt, by adding more of these counterions to it to make it become more elliptical. Anyway, so they're looking at elliptical micelles. It's kind of the same thing, and core shell structure. So it becomes a little bit. Anyway, there's a function for that, and it's going to have two sizes: this A size and this B size, instead of this just has R. And so, but it's basically the same idea. You're going to get this oscillation. One thing that's different is that between the A and B sizes, it's going to be a rod. So if these are largely different from each other, then you'd see a -1 power law would show up in here. Right? This would be like the B size, and that would be kind of the A size. And then you'd see the surface. So as you go smallest size, you just see the surface. Then you go down, oh, it's a tube. It's going to be dimension 1. And then it's going to have like a diameter. And then also on top of that, there'll be this perfect, if it's perfect length. If it was perfect length, then it would have oscillations here too, due to that. But basically, this length, I think, is a distribution, something like Johnson distribution. So it's not so much fixed in that direction. Anyway, so they have those. They have a function to deal with that business, the structure. The other source, that's kind of like, you have not perfect, then it's just going to be this decay. Then you have two reasons. One is the structure. Then the other reason is that they can organize, right? So this is like our diffraction pattern. It's like how Bragg's law is derived. So you're going to have these micelles. They have some charge, they repel each other, so they'll form a face-centered cubic structure or a hexagonal closest pact. They're just like a simple. So anyway, so they'll form one of those are the highest density, like 0.74 volume fraction. Volume to just fill in space 0.74 because they're basically touching spheres. So anyway, so that's definitely going to give, because that's got these planes that are going to give rise to a diffraction pattern, a real diffraction pattern. Okay, so that'll give peaks. So you have your D spacing, then you're going to have like the intensity, and it's going to have peaks in it that kind of decay. So you're going to have like Q, 2Q, if it's planes, and 3Q. If it's more complicated, you get other peaks. Right? Basically, that's going to be combined. Those sorts of peaks can be combined with these sorts of peaks. It's going to be combined with the original thing. So it gets a little involved. Like the patterns aren't going to be so simple. So that's where all this stuff comes from. But you can fit it. You know, there's functions that fit this stuff. So let's see. So this is this thing, this sine QR minus cosine QR divided by QR cubed. Forget about the arguments. That's the function for a sphere, and that gives rise to this kind of -4 power law. But this is the amplitude, and you square this to get the, so you see, you square it here to get the intensity out. So that's just a sphere function. And so that's like a popular function. So you have sine minus cosine. It's not written right. She screwed this up. Should be sine minus QR cosine. It's not sine minus cosine. So I mean, if you extrapolate to high Q, right, cosine is symmetric, right? So it'll have a value. Sine is asymmetric. In other words, if you go minus Q, sine's the negative of positive Q. So that cancels out. If you go large enough Q, there's nothing left. The plus and minus. But cosine, it's like 1 and 0, so it adds up to something when you go out. It's a damped function. So QR times cosine divided by QR cubed gives you 1 over QR squared. This one goes away, averaged at high Q. Then 1 over QR squared gives you 1 over Q to the 4. Right, so this thing will give you a power 4 at high Q. They do the expansion at low Q with a sine and cosine. There's missing a term here. There's a QR in front of the cosine. It's unfortunate that she forgot that. It's easy to miss it. But so that's just the sphere function. That's like the scattering function for a perfect sphere. So there's no correlations in that. Then the correlations come from this S of Q. So it's called the form factor. So that gives you the peaks due to the structure, the perfect structure. Right, and then this is called the structure factor, which has to do with how it's organized. And the structure factor, she doesn't say where it comes from. Right? She just, because it's complicated. She says she uses a Hayter-Pinfold structure factor, which is really complicated. The simpler ones to use. I think in this paper she doesn't say either. She does this. Oh, this one she uses. But that's not the structure factor. P of Q. I didn't really look at this one that closely, but anyway, that's that thing. Should get rid of this because that's. I'm trying to find a new program to do the web page. Apparently, it doesn't do files, right? So I put in here. This guy at NIST kind of wrote a book in scattering. I don't like the guy, but basically we got to use his book, you know, because it's the only one that's out there. It's kind of like sitting there. So this is how you deal with this kind of interaction thing for colloids, like we have charges, you know. So it's not for perfect crystals. So, and Ornstein-Zernike were the guys that did this, and they in the footnote to one of the papers on this is where that function, the scattering function, came from. The Ornstein-Zernike scattering function. But there's another Ornstein-Zernike function, which is this thing. Okay, so this is how you get the correlations of these things. Okay, so you have kind of a binary function that's going to describe the correlations. So binary correlations, and then you're going to have like higher order correlations. So the idea is like you have. So if you want to describe those correlations for the micelles, you have like two. You can say like they have some potential between them, but then if it gets crowded, then there's a third one. So that interaction of those two influences the interaction of like this guy with that one. Right. So the simplest thing is ternary, and there's going to be higher to that. It's going to go on and on. So you have the binary one you call C of R, and then this kind of influence of that these two associate, and that influences what that one is this H of R. And H of R influences C of R, so you take C of R plus H of R times C of R and integrate it over all whatever, and that gives you the total, like whatever of R, the potential. So that's Ornstein-Zernike's proposition. Seems kind of simple, but the problem is you can't you don't know, you can get what the binary one is, you don't know what this thing is, because in order to get this thing, you need to assume something about the system. So you have to you have to make some kind of assumption to make this thing work. Yeah.
If it was like arranged in like a perfect lattice, could you probably figure this out? Because you would know the structure.
Yeah, perfect lattice isn't a problem. The problem is if you have,
But if you have a colloidal solution, or you're
yeah,
like,
you have these things floating around, there's some potential between them. Then you need to figure out what's the total potential for a sea of a gazillion of these things. And then this thing, so he's kind of summarized this stuff here. So kind of this correlation function. So the correlation function we talked about, where you did figured out where the other thing is, and then do the double sum for the Polymer coil. Turns out for colloids, that's directly related to this potential of interaction by an exponential. So it's kind of like a Boltzmann function. You have the energy by KT, and this is like a probability. So probability is the Boltzmann expression. So this U of R is the thing you're trying to get. If you can get the potential, then you can get the G of R, then you can Fourier transform it and get the I of Q. So it's kind of like a series of steps, right? And the first step is this thing of doing this Ornstein-Zernike thing, right? And then in order to get this, you need to have what's called a closure relationship, because you want to do this integral. You don't know you don't know what the H of R is, and you don't know how it would influence C of R. So you have to say something to start with to kind of, so that the one that's used by the most popular thing is this, so they call them approximations. You make the assumptions of how this thing works. We don't need to go into the details of it because it's not going to be of any use to you. But basically, up to the point of that she's using the mean spherical approximation, which is the Hayter-Penfold thing. So Hayter is an Australian guy. Penfold's a British guy. And they met at Oxford somehow. And Hayter was kind of like the brains behind the operation. Hayter moved to the US. He became like head of the neutron thing at Oak Ridge. And Penfold stayed at Oxford. Oh wait, Penfold, this is the story, I'm remembering now. Penfold was Hayter's technician, okay, at Oxford. And he got a PhD under Hayter while he was being his technician. Anyway, and then Hayter moved to the US, and then he died, like he just died, up and died. He had like a huge stroke or something, or some blood vessel burst, and he just died. Like he was in like 50s. He just died at home, and then he didn't show up to work. And his secretary went and found him at his house dead. Right. So anyway, that's what happens if you follow this stuff too long. You know? Your brain burns out or something. But Hayter's a good guy. Penfold's a British guy. And then they were young, you know, I guess, when they did this stuff. So they came up with this equation. It's like this thing, that paper, that 81 has like 1,000 citations, like 980 or something. Depends where you look. So anyway, that's a pretty high citation paper. So everyone uses this thing. So it's got the terms in it that we mentioned, like the device screening length. This is kappa, or this is 1 over the device screening length. So that goes with the concentration and bar square root of that. And then it's got the Bejerum length in it. It's got the charge distribution along the chain, all the stuff for polyelectrolytes they use in this paper for that function in this thing. She listened here. So she ends up with anyway, oh, that's in this paper. So then she ends up with this equation. So you can look at that stuff if you want. Again, like it may or may not be of any importance to you, you know, but it will describe these kind of peaks and curves. So let's see. So she gives a crazy function, right? Let's see. That's, it would take you a really long time to figure out where it came from. So you have to kind of accept it, but you don't. I'm trying to find that function here, right? So this function. So it's kind of weird. This is one term. They do a page line break in the middle of the term. So it's kind of weird. But anyway, this is a constant. That's a Beaucage length. Alpha is like the degree of charging on the chains. That's kind of the A parameter, the spacing of the charges along the polyelectrolyte chain. Kappa is 1 over the Debye length. And then C is a constant. H is important here. Oh,
H is fixed at 12 angstrom.
right. H is the viral parameter. So it's like B2. So A2, so the second viral coefficient has units of volume. Right. So, I mean, anyway, it ends up being like excluded volume. Like we have V naught times 1 minus 2 chi, or 1/2 minus chi. So the chi is unitless because it's the energy over KT. Chi is a unitless number. So the prefactors is V naught, which becomes V naught originally was the excluded volume. So B2 becomes like the excluded volume. I'd say units of volume. It's like an excluded volume. So this H is B2. There's another way to do it. They call it A2, and the units aren't volume, and then that's kind of complicated. But basically, H you can think of as just excluded volume for the chain. So there's 8 parameters in here in the end, right? There's 8 parameters. So there's no hope of understanding or getting a physical feeling for what this thing's talking about. I mean, maybe you could after a while, but what you want to do is say like, okay, does it follow Guinier's law? Right? Or does it follow some power law that's of meaning? So polyelectrolyte is going to go to a rod. It should have a power of 1, right? It should be a 1. So does this go to 1? Well, so you say really high Q, you can forget about kappa, just have Q squared, and then Q's big, so you can forget about the 1, forget about kappa. Then you have another Q squared, so Q's big, so you end up with Q squared over Q4. So you end up with Gaussian power law IQ. So that fails. I mean, just glancing at it, you can say this doesn't describe a polyelectrolyte. Not even if it was flexible somehow, it would be 5/3. Right? There's no possibility polyelectrolyte would be 2, -2, like 2-dimensional. It doesn't exist. It would be 1-dimensional probably. And then when Q is small, what you can do is take all these things. So if Q is small, then you use this thing. So I haven't done this, but we say exponential of something is 1 minus that thing.
Oh, you gotta switch the camera.
Oh, sorry. Okay, so 1 minus the thing plus the thing squared over 2, everything's over factorial, but 1 factorial is 1, 2 factorial is 2, minus x cubed over 3 factorial. So it keeps going like that. If it's negative, it's basically it's the same if it's anyway. So whatever. So if x is small, then you can kind of forget about those and you just have that. So if you have like k minus k to x, then that's basically exponential minus x somehow. So you can kind of say, I haven't done this, but basically, so this is going to be exponential kind of q squared. This is going to be something like exponential q squared. That's going to be exponential q squared. And then plus 1. So you're not going to get Guinier's law out of this thing, I don't think. So q to the 4, you can multiply this out, you get 1 plus q to the 4, because if q is small, you get q squared out of this thing, because q is small, then only the small lowest order term would last. So this thing would give you exponential q squared, the total thing, times some constant. And this thing gives you exponential q squared. I don't think you're going to get Guinier's law out of this, but you could try. See if you can get Guinier's law. The main rule is that exponential expansion rule. and see how that, basically this thing has to give you Guinéa's law if it's a true function. It doesn't give you the right power law. It gives you a power law, but not the right one. Then I don't know, you can try to get Guinéa's law out of it. I don't think it'll give it to you. And then then the prefactors have to kind of match up so that it works. My hunch is that this thing is bogus because it's too complicated and there's no explanation given for it at all. So it's just like, here's this thing.
Do they have any kind of citation of where they're getting this from? Or they just,
Yeah, they do, but you can't get, it's at, oh, let's see, 44 and 45. I think it's their
previous paper.
I think so. Wait, I did look at it. I don't remember though. That's a good point. No, it's not them. It's 88. It's these two, right?
Mhm.
Candau's a pretty famous French guy. And this is in Journal of Physics. This is a French journal. Journal de Physique. It looks like Journal of Physics is Journal de Physique. Anyway, you can get that. So, yeah, it's these two. I don't know, Candau's a good guy. I don't know these people. So 88 and 93. So Candau is the last one to use it. So maybe it's okay. I don't know. It's kind of like going down. It isn't, but it isn't really well thought out, I think, the way they're doing things here. They claim that they verify. The other thing is like they claim that they verify the third structure for this thing. So, oh, not this. They claim in this one, this is the 2014 paper, but this they're claiming that by adding alcohol you can release the grapes and the grapevine. They kind of automatically pick the grapes, which could be. I mean, you could think about like drug delivery or something, or maybe it's like how proteins are released from the ribosome. This one they claim to demonstrate this one's true out of these different options. So the hairy micelle thing is kind of a neat idea, so I don't know, could be useful, or it might just be something insignificant. It's not, it's like okay journals, they aren't great journals. Actually, this is a good journal. This is a pretty highly cited journal, and this one's like lower grade, although this is an ACS journal and that's like something else. There's Elsevier, so Elsevier is like a kind of a lower, less regarded publishing group, although this journal has a higher citation index than that one. I think this one's like 8 and this thing's like 4, so it's hard to tell. But that's about it, I guess, for this. Let me see what so it's kind of like just fish around this thing and look at the scattering functions and see if you can kind of critique what people are doing. Extrapolate. This is summation appropriate. I mean, I think you can pretty clearly see that it isn't, but then where does this come from? So this means you have to get the Guinéa's law for the Bernstein-Zernicke equation and Guinéa's law for Debye and compare the two, and then you can get this expression. That's in the PowerPoint. That's already done. If you want to just look there, then this thing just shows that they haven't looked at their own data, and they're using random functions that have nothing to do with what the data tells them. And obviously that this thing won't be a Gaussian. And there's functions that could describe it properly, but they aren't using them. So, and then this thing is like extrapolate those, just what I said, like the high Q is going to come out power 2, and then try to get Guinea's law from it. If you can't, then that means it's a bogus function. Like if you can't get Guinea's law, it's not a good function. So this is how you can take something so complicated that you can't possibly understand it, or maybe you could after a month. You can save yourself a month of trying to figure it out and just say like this equation isn't doing the right thing at all, you know. So it's not a point in looking at it. So things have to be like the correlation function has to be symmetric. You know, certain things is like rules to live by. So if it, and you can waste a lot of time chasing after a lot of different things. So it's good to be able to just say like quickly, like that's bogus, and just move on. You know? So, all right. So there's a lot of functions in the world. You know, it's like can't spend time on all of them. So that's it. I think that's about that stuff. You know. If you want, I mean, there's this thing you can glance at it. Supposedly this is a dumbed down version of, but it isn't really. So Hamuda was like a postdoc or graduate student of a guy named Benoit in France. So France has this Algerian problem. You know, they decided that they wanted to own some parts of Africa. Then they had kind of a Vietnam War in Algeria in the 1960s that the US managed to totally ignore it, you know, even though they were like doing really nasty stuff. They also started the Vietnam War too. It's like French have a long track history of doing nasty things, but anyway, also the French are stupid, okay? So they made anybody in their colonies a citizen of France, just like the Romans did, I guess, because they want to be like the Romans, you know, except with the French accent. So the Algerians all moved to Paris. You know? So Paris is just like flooded with Algerians, and the French are like Nazis, half of them. The Vichy French in the south, like basically Nazis, kind of. You know, they aren't like the north part; they're more liberal. Anyway, so they all of a sudden they're flooded with these Africans, and they that's what the problem in France is now, that they're like groups of people. It's their own stupidity. It's a combination of cruelty and stupidity, you know, coming back to haunt them. That and they're 80% nuclear power in France, okay? And they have no uranium at all. So it all has to come from Chad. So it means they have to have an army in France to protect their energy in France. Otherwise, the whole electric system shuts down. And they're not willing to pay the price of whatever it would cost to just buy it from them or something, you know. Anyway, there's a lot of problems in the world, but anyway, Benoit was a good guy, really smart. Hamuda was an Algerian that went to work for him and then came to the US, works at NIST. He put together this book on scattering. He's like a physics guy, you know. So he did a course. He does a course. It's like a course you can sign up for. Then he's got a book to go along with the course. You can do it online. I think you can do it at your own time. You can get credit for it at UC. I think if you beg somebody, if you want to. You know. I've had students do it. I take this course. One student, I shouldn't say students, and she enjoyed it. She got stuff out of it. So Benoit really published a lot of great stuff. He was really one of the stellar people, seminal people in scattering. I don't know if he's dead though. I shouldn't probably say he was, you know, but I don't really know what his fate was. But it was a while ago. He actually worked a lot with that Julia Higgins from the other thing, the Dane from London. So anyway, so Hamuda's in that bloodline. You know, so and this is probably good. You can see there's questions and answers. That's from that course. This other stuff, I took a while to find, because when it's open-ended, it's hard to find papers. Like there's too many. So I put some other scattering papers here. If you want to take a look at them, you can. There's some stuff on conductive polymers. Any of them look interesting, I can go through them. There's one paper on looking at PVME, this kind of blob formation in water. When you heat it up, they kind of use light scattering to do it, picosecond resolution. scattering and an extensional rheology chain stretching out and some other things, but you can glance at those if you want. There's one on conductive polymers and the Seebeck effect, because I was talking about that with thermocouples, but I thought that was kind of interesting. But anyway, I didn't use those, so. All right, so you can quit there for the weekend. It's just questions.
Do you know of any, so like there's all these equations that, like the Ornstein-Zernike and all that, they all seem to have an issue of either they don't follow Gounier's law or they aren't symmetric. Are there any actual, like, somebody's come up with an equation that kind of satisfies both of that? Or I'm missing something?
Well, yeah, I mean, the Debye equation does for polymer chain, right?
Yeah.
And Benoit actually had an equation for any fractal, but it's an integral equation. So it doesn't have a discrete answer.
So that's why people use these other equations, because they're easier
I
to
mean,
use.
originally, yeah, but basically nowadays, like on your cell phone, you can do the integral. Right? So like, there's no reason not to just do the
Just plug it into
integral. now.
Wolfram, it's like, oh, hey, I got a.
Yeah, I mean, you can just do it. You can literally do it on your cell phone, but easily with a PC, you can do these integral. So every time you
And
get a
if
point,
it's more complicated, then you have a university computer that can crunch through it.
yeah, but you don't need it. You can do it literally on your cell phone, you know? So I mean, there's no point, at some point you just do the integral.
There's no point in making a simplified equation. when you
Yeah,
can
they're
solve
using the
integral.
simplified equation that's wrong, and there's the actual equation, and you can just use it, you know, there isn't a reason not to do the integral. The thing is, like, every point, so every iteration, you're gonna do at least squares. So you're gonna do a calculation, subtract your data, square it, sum all of them, then minimize that. So, but for each point, you have to do an integral of like 1,000 points, which takes a less
Takes
than
a,
no
takes a
time.
second,
No,
but
it doesn't take any time at all. It can do that like you don't even notice. You can do 1,000,000 of those in a second, you know, or 1,000,000,000 of them in a second. You know, with if you have a Mac M1,
yeah,
whatever.
maybe
you know.
not on my cell phone, a billion of them.
It's
but-
actually the reason that everyone's paying $4,000 for computers. You know, it's like, and no one uses it. So, it's like,
They just use it to go watch YouTube videos and stuff like that, right?
yeah,